Perfect. So the title of the presentation is Solid State Additive Manufacturing Enabled by Kinetic Energy. The speaker is Professor Sara Bagherifard, as I already mentioned. And so it's a pleasure to guest your plenary speech now. Thank you.
Thank you very much. Good morning, everyone. Thank you very much, Filippo. I would like to start by thanking the organizing committee for this invitation. My talk is about solid state additive manufacturing enabled by kinetic energy. So it's a technology a little bit different from the common technologies that we use for additive manufacturing that are based on fusion and solidification of the material. So I would start with a brief introduction about the technology that I'm using as the solid state deposition technique. It's called cold spray. Cold spray is a non-thermal deposition technique in which small particles are accelerated by a supersonic gas. They impact the substrate at very high velocities, and because of the high kinetic energy, they get severely plastically deformed. They adhere to the substrate, and then they would build up the layer. The main, let's say, intrinsic characteristic of cold spray is that you can spray almost any metallic material mixed with each other, or also mixed with ceramic materials at temperatures that are much lower than the melting temperature of any material that is involved in the process. So that would give us a lot of flexibility in terms of selection of the material, mixing different materials, using materials that are oxygen sensitive or temperature sensitive. In the area of cold spray, that was born as a coating deposition technique, we've been working on numerical and experimental techniques for identifying the required parameters for deposition of the parts, fatigue strength of coated samples, nanocrystallized coating, and so on. But today I'm going to talk mainly about the latest trend in the area of cold spray, that is additive manufacturing. Before that, just a few words about what happens during bonding in cold spray. We normally need to reach a special window of deposition. So it's in terms of the range of velocity in order to ensure that the particles are bonding. So at velocities lower than this critical velocity, which is a function of thermomechanical properties of the material that we are spraying, we have the rebond of the particle. Then we would start bonding at critical velocity, slightly higher than critical velocity. We can get to full deposition efficiency. It means that all the powder that we are depositing would fully adhere, so we are not losing any powder during the process. And as we increase the velocity further, we get to the range of eroding the substrate and removing material. So it's very important to identify the window of deposition for the material that we are trying to spray based on its thermomechanical properties and the properties of the substrate material. Why we are pushing cold spray for additive manufacturing? So cold spray, as I mentioned, has been established as a coating deposition technique, but there are a set of parameters that would promote its application for additive manufacturing. First of all, there's no theoretical limit for the thickness of the deposit that we can have. We can start from few hundreds of micrometers to a couple of centimeters. We can get very high production rate, much higher compared to other additive manufacturing techniques. In comparison, let's say with laser powder bed fusion, we can get 20 times higher deposition rate. Much high density, very homogeneous structure, and high cohesive strength. We get compressive residual stresses because of the pinning effect and the plastic deformation, rather than the tensile residual stresses that we normally have in thermal-based additive manufacturing techniques. We have, of course, the low temperature. We are way far from the melting temperature of any material that is involved, so we would avoid all the problems regarding, let's say, the grain growth, undesired phase transformation, oxidation, crystallization, all the problems that are coming with the melting and solidification of the material. So that would give us a lot of flexibility. And we can, because of that, we can also easily mix different type of materials. We are not bounded with their affinity of the thermal properties of the materials that we are mixing. And we can get, let's say, multifunctional structures. However, there are still a lot of challenges that have hindered the establishment of cold spray as an additive manufacturing. I have listed few of them here that I'm going to touch briefly during my talk. First of all, we don't know whether we can use cold spray also, not just for, let's say, geometrical restoration on non-load-bearing components, but whether in terms of structural integrity, they were also efficient and comparable with other additive manufactured materials. How shall we correlate the process parameters, including the gas temperature, the gas pressure, the kinetic parameters of the robot, and so on, with the performance and mechanical indexes of the deposit? If you are mixing different powders, and in the feedstock we have specific volume fraction, how we can correlate that to the volume fraction and the, let's say, chemical composition that we have in the deposit? And then last but not least, how we can control the shape in cold spray additive manufacturing. That's probably one of the most important parts, because in additive manufacturing, we need to have control on the shape. Otherwise, we are very limited and not, let's say, competitive in the area of additive manufacturing. So I would start with the first topic, which is about the structural integrity of additive manufactured parts that are made by cold spray. We have done some research in this area, getting some thick coatings and then separating the classic dog bones from the deposits. We have performed tensile tests on the cold spray additive manufactured samples and compared them with laser powder bed fusion or SLM samples made from the same powder. After the proper heat treatment, you can see the results for static tests are comparable between SLM and cold spray. And here you can see the results also for actual fatigue tests of the samples that were comparing the results for SLM and cold spray, very comparable fatigue limit at room temperature. Also, the results compared with, let's say, bulk cast material that are obtained with classic manufacturing techniques are in line with what we could get for these samples, which were Inconel 718. Here you can see also the results for 316L. Again, the microstructure of the cold spray sample, where you can see the classic, let's say, packing of the pancakes, the powders that are flattened on top of each other. After annealing, the boundaries are a little bit more fading, and we are promoting the metallurgical bonding. And then after heaping, we are almost recrystallizing the structure. Here are the response of the tensile response, static tensile response of the samples. In as-built condition, we have quite very low ductility, very brittle behavior, but after annealing and heaping, we are recovering a notable ductility. In terms of porosity, with different methods and different configurations, we are always 1% porosity. And here are the results for the fatigue test of our samples, the actual fatigue test, that are comparable and in line with laser powder bed fusion data that we could find in the literature with different process parameters. We have performed also in collaboration with our colleagues in IPP in Prague, crack propagation test on our samples, forcing the crack to propagate in different directions in order to see whether if we have any anisotropy inside the cold spray samples. In as a sprayed condition, we have some anisotropy because the way the particles are packed are affecting the crack propagation. But after annealing, the results that we could get are very similar to the data for the rolled sheet. So very similar to bulk material that we can get with other additive manufacturing techniques. These data would confirm the high potential of cold spray to be used for structural components as an additive manufacturing technique, and not just for, let's say, coating or geometrical restoration or for non-load bearing components. The next topic I would like to briefly touch is how to correlate the process parameters to the mechanical performance of the structure. We have, it's very useful to be able to mix different materials for different purposes. What we have done in our group is that we have sprayed mixtures of or blended powder for surface functionalization, for using one powder as a porogen in order to remove and get a porous structure, or modulating the mechanical response because of the synergy of between two materials that have very different mechanical properties, or for, let's say, corrosion or wear resistant. But there's one big issue when we are mixing different materials, is that since the process parameters are unique, they could be more favorable for the adhesion of one particle rather than the other. And that's why when we are mixing two powders, let's say in a 50-50 volume fraction, what we get in the deposit can be very different from 50-50. So it's very important to be able to predict and estimate what we have in the deposit based on the blended powder. There are a lot of, let's say, different mechanisms playing around here, because we have the probability, for example, if you are mixing two different powders of A and B, during spraying, we have the probability of powder A impacting a powder A or B, and vice versa again for B impacting A or B impacting B, and their mutual interaction also with the substrate. So there is a very complex mechanism, including, let's say, affected by the thermomechanical properties of each single particle and how they interact with each other and with the substrate. We have developed a hybrid experimental, numerical, and probabilistic method in order to be able to estimate the deposition efficiency and the chemical composition of the deposit when we are mixing different powders. So starting from a single particle impact in order to obtain the flattening ratio and the area that would be covered by a single particle, performing a series of experimental tests to find the probability of adhesion of each particle to the same material or to the other material or to the substrate, so the mutual interaction. And then we have developed a semi-empirical probability-based method that would bring all together in order to give us the possibility of estimating the deposition efficiency in terms of volume fraction of each material that we have in the deposit, and its evolution is variation as we are getting far from the substrate. Close to the substrate, we have also the interaction with the substrate, so we have a transient condition in terms of chemical composition, and as we get far from that, the chemical composition becomes more stable. Here is a schematic of the semi-empirical probability-based method that we have developed. So we are getting the input data in terms of the area that would be covered by each material, the probability of adhesion of each material to the other or to the substrate. And then in an iterative approach, we are considering the area that would be covered by each material in order to get the overall chemical composition. Here you can see the results of application of this model to a specific combination of zinc and aluminum for 4 different chemical composition. The results are in very good agreement with the experimental measurements. And also here you can see the results in terms of capturing the variation and evolution of chemical composition as we are getting far from the substrate. In this case, for example, for an steel substrate, we have higher probability of aluminum to adhere to the substrate rather than zinc. So we have higher chemical composition of aluminum close to the substrate, and then it's changing as we are getting far from the substrate at a distance of 300, 400 micrometer. We are getting to the stabilized chemical composition that can be captured very well with this predictive model. In a few slides about the numerical simulation of the deposition process that is giving us a possibility of estimating the mechanical indexes of the material or physical indexes of the material. We have analyzed very different, let's say, range of numerical models that would give us a possibility of modeling the process with high fidelity. We have used Lagrangian, coupled Eurasian, Lagrangian, and smooth particle hydrodynamics in order to perform single particle and multiple particle models, and to include, let's say, the effect of various primary and secondary parameters of the process, which include gas pressure and temperature, the powder parameters, that is size of the powder, size of the particle, morphology of the particle, velocity and the angle of impact, and then the secondary parameters that are more related to the movement of the nozzle that is moving the head and the gun of the spraying, so traverse speed, hatching distance, standoff distance, and so on. I'm not going into the details, but just showing you a framework about a numerical model that we have developed. For example, in this case, for checking the effect of the particle characteristics on different quality indexes of the deposit. Here we have performed single particle analysis in order to see the effect of the particle morphology, considering a range of, let's say, regular and irregular geometries with different angles of impact, the effect of the thickness of the oxide layer around the particles, the effect of the deposition angle, and the effect of the substrate properties on critical velocity, which is probably the most important parameter that guarantees adhesion of the particles to the substrate during cold spray, and also on multiple particle impacts in order to see the effect of all these parameters on the porosity of the deposit that we can during cold spray, the angle of impact, and the morphology, how they affect the porosity. We have validated the model using, let's say, some experimental tests to see the effect of particle size on particle velocity, critical velocity, effect of substrate hardness on the critical velocity or angle of impact on critical velocity. And once it's validated, we have used it to estimate different quality indexes. In this case, you can see, for example, the effect of particle morphology. We consider, let's say, two typical, very ordered and regular geometries. And then these, let's say, representative shapes for irregular geometries, considering all possible, let's say, rotation angles of impact for each of these shapes, and see how they would affect the critical velocity, or they would affect the overall porosity that we get when we have multiple particle impacts. So this model has the possibility of being used as a, let's say, tool for to start the experiments with an educated guess when we are trying to optimize the parameters, depending on the type of the material, the type of the powder, the substrate material, and so on. The last topic that I would like to briefly touch is shape prediction in cold spray. So we have been bragging about the possibility of using cold spray for structural applications. It has comparable fatigue performance with respect to other additive manufacturing techniques. There's no size limit. There is very high production rate. So these are, let's say, what is differentiating cold spray with respect to other additive manufacturing technologies, apart from the fact that we have very lower heat input. But one of the main bottlenecks of cold spray that has hindered its, let's say, establishment as an additive manufacturing is that we still have inadequate geometrical control. Because, I mean, the main point of additive manufacturing is to get very complex shapes, have geometrical flexibility, but this is not the case yet for cold spray. So despite all the, let's say, advantages that it has, it's still very limited in terms of shape control. It's very good for very large sizes, but then if we have very, let's say, complex features, then we need to definitely use a post-processing technique. So we've been working in this area in order to get how much we can get control on the shape. The problem of the shape control for cold spray is that as we are spraying using, let's say, an axisymmetric commercially available nozzle, because of the distribution of the particles in the flow, when using, let's say, low number of tracks or low velocity, high velocity for the nozzle transfer speed, we typically, not always, but typically get a Gaussian distribution. As we are increasing the number of tracks or we are decreasing the transfer speed of the nozzle, that would evolve into a triangular shape. So this is causing, let's say, the problem for the shape control, because we cannot simply superimpose these triangles to each other because of the dynamic of the process and the flow of the particles. And then that would become, let's say, a challenge in order to define a target, to reach to a target geometry. What we have done in this area is that we started from a model that was developed by Professor Klinkov a long time ago, considering, let's say, the physics of the process and the distribution of the particles in the flow, and upgraded this model by adding additional features to give it much more flexibility in terms of the shape of the substrate, in terms of the trajectory of the nozzle, and the, let's say, different parameters that would affect the shape prediction. So the model is based on considering the deposition efficiency as a function of the angle of impact, considering deposition efficiency as a function of the standoff distance with respect to the substrate, and is generally, let's say, considering the particles distribution profile as a Gaussian based function, but we have the possibility of implementing any other type of function inside the model. So we get to a series of partial differential equations that is based on the physics of the process of the deposition, and is able to predict the shape of the track as a function of different process parameters that we have in the process. Here you can see the results that we could get from this analytical model for two different materials, Ti64 and copper. capturing, as you can see, the effect of the variation of the shape in terms of the shape and the height and the width of the profile as the number of the passes are increasing. So we started from here, you can see for TI-64 starting from 10 passes up to 20, and you can see even much more clear the variation from the Gaussian shape to the triangular shape for the case of the copper. So the model can, with very high fidelity, capture the shape as the number of the passes is increasing. Here you see the prediction of the model for the effect of spray angle, as we are changing the angle of the nozzle with respect to the substrate. And here are the results from the, let's say, the experimental data that has been digitalized in 2D and 3D. Very good match also in terms of spray angle. The effect of scanning speed and spray distance. Again, all these parameters are affecting the shape, the height, and the width of the deposit. So the model is able to get also this data with a very good fidelity, and also the effect of superposition of different tracks or using a curved shape substrate and how much it would affect the shape of the deposit as we are increasing the number of the passes. So the analytical model that has been developed has a very high potential to capture the shape and evolution of the shape of the track, as we are changing different process parameters, including angle of impact, including number of passes, standoff distance, and velocity of the nozzle. However, although it has a very high fidelity in terms of the prediction, it's a very long process. So if we want to superimpose many different tracks and use, let's say, this analytical model for rapid prototyping, we need to pair it with some deep learning approaches in order to be able to fasten, let's say, the whole process and give us the possibility of optimizing many different parameters and implementing many different parameters in the process. So we have very recently started in pairing the analytical model that was originally developed in our team with these deep learning approaches. Started with this for TI-64 with the full factorial method, implementing, let's say, running the analytical model for all these, let's say, series of parameters in order to create the data set that we need for the deep learning approach. So the parameters that we have started implementing for now are the number of the passes, standoff distance, spray angle, transfer speed, and of course parallel tracks. And we have developed two different, let's say, architectures of deep neural networks for 2D and 3D prediction of the shape as we are implementing all these, let's say, parameters. Here's just one example for a shape that we have considered for the, let's say, as our target shape. This is the analytical model prediction, and this is the prediction of the DNN model that is a fraction of the time with respect to our analytical model. So this would give us the possibility of optimizing many different parameters and adding additional functions to the process. This is what we have started already to implement in the model, trying to optimize the hatching distance in order to minimize the let's say, the waviness of the top surface that we get and minimize the surface softness to get better surface softness quality. We are optimizing the scanning strategy also for the cross sections to get higher geometrical accuracy and minimize also the number of the variation in the nozzle direction in order to minimize the acceleration and deceleration of the nozzle that would affect the quality of the geometry. And also we are implementing another function for adaptive slicing to again optimize or improve the geometrical fidelity as we have different small features in the structure. So this is an ongoing research, and we hope to be able to get more, let's say, geometrical control as we are working with cold spray. And just last few slides, we are implementing this approach not just for additive manufacturing, but also for local repair and welding in some structures. So we have considered some local defects, let's say enclosed or true defects, or even for welding different geometries. And we have started implementing the analytical code in order to get our trajectories, design the trajectory for repairing in order to minimize the time and minimize the excess material that should be removed after repairing. And the next step would be to correlate this geometry to the mechanical properties or physical parameters of the structure. So I would like then to include, we have established the high potential of cold spray to be used for structural application in additive manufacturing. We have developed a hybrid framework that is able to give us to predict, let's say, the chemical yield as we are mixing different materials. And that would give us much flexibility to take benefit from the heterogeneity that we can get as we are mixing different materials to break the trade-off between competing properties. We are proceeding with the shape prediction for additive manufacturing and also repair. And the welding and future plan is to correlate the shape to the mechanical properties like porosity, residual stresses, and then to the mechanical performance of the structure. I would like to thank the contribution of PhD and graduate student, academic and industrial collaborators who contributed to the results that I presented in today's talk. And that's all. Thank you very much for your attention. I would be happy to answer your questions.
Thank you so much, Sara, for the excellent overview about this topic. We have time for a few questions, so please. Yes.
Thank you, Sara, for your excellent talk. Cold spraying resembles a little bit, in my opinion, to shot peening. So I was wondering if there are similar effects to the substrate in terms of grain refinement and residual stresses.
Very good question, Matteo. What happens during cold spray that you have the peening effect, like what happens in shot peening, because we have very high velocity particles that are impacting the substrate, but we have also the effect of the heated gas. So the particles are not much heated, but we have the heated gas as it's expanding, it's cooling, but still there is some effect for that. So there is a combination of different parameters that would affect the distribution of residual stresses that we get. So the residual stresses that we get is slightly lower than what we get compared to shot peening, because we have, let's say, the contribution of the peening, the thermal, let's say, annealing of the process, and also the affinity in terms of the coefficient of thermal expansion of the particles and the substrate that are adhering to each other would somehow affect the distribution of residual stresses. So in some terms, we get, yes, compressive residual stresses, but the magnitude of the compressive residual stresses that we get are lower than cold spray, than shot peening. Yeah. You're welcome.
Thank you so much. Yes, Jan.
Hello, thank you very much for a very interesting talk. I was wondering, you showed some chemical changes proceeding from the substrate towards the end of the part, so to say, the surface. Is this the Kirkendall effect? And is your model based on diffusion, or was it, is there something else going on? Because you said it's cold spray, so I'm guessing the substrate is not under heat.
Yeah, the fact is that we are mixing two different powders here. Mm-hmm. So it's not the chemical variation of the particles, it's the distribution of the different materials. So the chemical composition is changing, not because there is some diffusion happening during the process, it's because one powder is more favorable to adhere to the substrate. For example, when we are mixing aluminum and zinc, aluminum would adhere more easily to the substrate rather than zinc. So we'll have a higher composition of aluminum very close to the substrate. And as we are getting far from that, then we will get to a more stable situation. So it's based on the deposition efficiency of different individual, let's say, particles that are inside the blend. It's not a online chemical, let's say, variation in terms of the chemical, let's say, variation in terms of reactions that are happening, but the possibility of adhering one particle rather than the other to the substrate. So it's a probability-based, let's say, in terms of bonding, which material is more, let's say, prone to bond to the substrate rather than the other. Okay.
Thank you.
You're welcome.